Hey guys, my name is Pedram and I'm a professional practice assistant professor in finance. I'm also a CFA charter holder. This is another episode of my crash course in machine learning concepts, simply explained. Alright, part 12, polynomial regression in machine learning. So if you haven't watched part 11 yet, make sure that you watch it first and then you watch part 12, because in part 11 we talk about linear regression models in general. Now, polynomial models are basically supervised machine learning algorithm and are an extension to our linear regression model. So we put them in the same category, linear/polynomial regression models. Now let's see what is polynomial regression model. The polynomial regression model is a special case of multiple linear regression model. Let's see how we can construct that. Do you remember from our linear regression model, we had f of w and b. It was a function of x, right? So we said b, our bias term, plus weight 1 multiply feature 1 plus weight 2 multiply feature 2, and etc. Right? So here, if we assume that, okay, feature 1 is x, feature 2 is x squared, feature 3 is x to the power of 3, and etc., then this is basically what we call polynomial regression model, right? So for example, you can think of one of those features. Imagine we have education, right? If I add education to the power of 2 to the model, to the power of 3, 4, and etc., this is our polynomial regression model. So what is really important in polynomial regression models is that we are not really interested in the coefficients themselves, right? I.e., we are not interested in interpreting this model, because what if I have, let's say, education to the power of 5, to the power of 6, to the power of 10? There is basically no way or no point to interpret that coefficient, right? And in general, this is a machine learning model that's mostly used for predictions rather than the interpretation, right? And let's see what are the variables here. So W is our d-dimensional vector of parameters. So we are going to have basically d parameters, W1, W2 up until WD. And B is our bias term, which is a real number. And D here is a new thing, right? We didn't see D in our linear regression model. And that's actually what we call hyperparameter. Hyperparameter. So this model is going to have both parameters, W's and B, and hyperparameter. And it's also, as we discussed it earlier in the linear regression model, it's also a parametric model. Why? Because we're imposing a functional form to the data, right, to the model. So the functional form is something like this: wx plus w2x2 plus w3x cubed, and etc. So we are imposing this functional form. So for that reason, it's going to be a parametric model, which has both parameters and one hyperparameter, which is d. D is the polynomial degree of the model, and we call it hyperparameter. So what is the difference between parameters and hyperparameters? I think in earlier videos I talked about it, but let me quickly remind you. So when you have a test set and train set, imagine this is a data, this is your train set, and this is your test set, right? You're going to use a train set, the machine is going to use a train set to learn the pattern in the data, to train the model. By training the model, the machine is going to learn the parameters, W star and B star. However, before even training the model, we have to start with some pre-specified value for our hyperparameter. So let's say D. D1. D1 is going to be, I don't know, one number. Let's say, we are going to make an example that the number of polynomial degree, let's say D is equal to 5, right? And then we start training the model with that. So we're going to figure out 5 W stars and 1 B star, right? And then after that, when the model is trained based on some pre-specified value for hyperparameters, we're going to make predictions in the test set. We call it y hat. And after that, we're going to use the performance metrics to report the numbers in the test set, right? So let's say R score in the test set, RMSE in the test set. So I want you to be aware that this D at the very initial run is going to be pre-specified, but afterward we're going to optimize that D itself by using cross-validation. Okay, so make sure that you watch the videos when I talk about cross-validation and tuning hyperparameters. All right. So what is the optimization problem for polynomial regression model? The optimization problem is going to be exactly the same as for the problem in the linear regression model, right? So basically we are minimizing the mean squared error over W's and B, right? So basically we are minimizing the errors, square them, and then take the average. And this function is going to be exactly the same as the loss function in linear regression model. So what does it mean? It means that it's going to be well behaved. It is continuous, differentiable at any point, and we can use either OLS or simply our gradient descent. So the idea is that for this optimization problem, there's also a closed form solution, So we don't need to necessarily use some sort of numerical optimizers like gradient descent or stochastic gradient descent. But if you want, you can. So the solution to this optimization problem is going to be W stars and B star. And now that we have the W star and B star, you can specify your f hat of x and make predictions based on that. So we are ready to make predictions. So on the right, we are looking at the data sets versus polynomial regression model fits, right? So imagine this purple dots are the raw data, and now we're going to use 3 different models to fit the model to the data, right? All right. So the first one is when the value of hyperparameter is equal to 3. So when d is equal to 3, we're talking about this red curve, right? As you can see, it is capturing the relatively upward sloping relationship in the dots in the data, but it's kind of missing out let's say the seasonality in the data, the going ups and downs in the data, right? So maybe we need to increase the polynomial degree. So if we increase the polynomial degree to 5, we get something like this. So here d is equal to 5. So 5 is going to be more flexible. As you increase the degree of polynomial, you're making the model more flexible, right? And then you can say, okay, let's increase it to 9. If we increase the polynomial degree to 9, it's going to be a lot more flexible. In this example, it's not a bad idea to make the model more flexible because it's capturing let's say, the true relationship in the data. However, one of the caveats of polynomial regression model is that it can overfit. It can overfit, and then we're going to talk about it, how to avoid those overfitting. So how do we avoid overfitting in polynomial models? We're going to do that by tuning the hyperparameter d in the model. Remember, d was the hyperparameter and was the degree of polynomial, right? Let's look at a very simple example. Imagine these dots are the true data. So the true data are basically the blue dots that we see. And the blue curve here is going to be the true relationship. I call it true f of x. This is the true relationship in the data. And remember, guys, this true relationship is unobservable. And in machine learning, we are trying to estimate, get as close as possible to this unobserved relationship, right? We're going to estimate that function. And now, let's plot RMSE. This is the performance metric that we used in linear regression. So we're going to use the same performance metric in the polynomial regression, because basically we're looking at regression analysis, right? Y minus y hat. So we can talk about mean squared or RMSE, the root mean squared error, right? So if I plot RMSE in the test set versus the model complexity, so let's call this one model complexity, which is a function of d, right? So let's say here is simply d, right? If d is equal to 1, the model is very simple. If d is equal to a large number, let's say 10, the model is more complex, right? So it's simple. As we go from left to right, the model is going to become more complex. So this is a simple model. All right, now let's try to, roughly speaking, visualize this plot, right? So imagine we start from here when d is equal to 1. So if d is equal to 1, look at this line. So we're going to get a linear regression, and the fit is also line because it's to the polynomial to the power of 1. And as you can see, well, the model is this model with polynomial degree 1 is not capturing the true relationship in the data. We know that the true relationship is curvature, but this is some simple line. So the RMSE in the test set is going to be large, right? So let's say this is the RMSE. So this is for d is equal to 1. Let's say here d is equal to 3, and here d is equal to, I don't know, maybe 9, right? And we have here d is equal to 2, d is equal to 3, and maybe d is equal to 9 is here. Okay. And as we increase the degree of polynomial, then the model is going to become more flexible, more complex. It's going to be able to fit the data better. So if the model fit the data better, the errors are going to reduce. If the error reduce, the MSE is going to get smaller. If the MSE decrease, the RMSE is going to decrease. So as we can see, when we make the model more complex, the RMSE is going to decrease, right? And as we make the model even more complex, in this specific example, it seems that the RMSE is also decreasing. So when d is equal to 3, we have a very relatively good fit to the model, right? But as we increase the complexity of the model, it comes at a cost, because let's look at this exaggerated version. So here, this is our model, right? The fit is very nonlinear. And we know that, yes, maybe it's performing a good job. Actually, here is doing a perfect job in the train set. But remember, this is machine learning. We're not interested in the performance in the train set. We are looking at the performance of the model in the test set, something that the model has not seen before. So this means that if I take this green curve and throw the test set at it, so maybe the test set is going to be something like this. And as you can see, the model is going to be way off in the test set. And for that reason, the RMSE in the test set is going to increase. So in general, we see a kind of U shape or elbow shape when you're plotting the RMSE of the test set with respect to the complexity of the polynomial regression model. And the optimal value of polynomial degree, or the optimal value of hyperparameter, is going to be wherever it's going to minimize the RMSE. So here in this simple example, the answer was 3. So we know that this, when hyperparameter, the optimal version is 3, we get a best combination of model bias and model variance, right? So this is RMSE of the test set with respect to degree of polynomial. If I ask you, can you plot the RMSE in the train set, what's your guess? Yeah, in the train set, the RMSE is going to always decrease, right? As you make the model more complex, it's the RMSE in the train set is going to shrink. So that's why we don't focus on RMSE of the train set using machine learning model, right? We focus on something that the model has not seen before. So this is the RMSE calculating in a test set. We also report RMSE in the cross-validation version, cross-validated data. So you may see RMSE cross-validation. And if you watch the video that I covered the cross-validation concept, we said that we do it for 2 reasons, right? First, we use cross-validation for tuning the hyperparameter, so this is the application. And second, we want to make sure that we are looking at the performance of the model in something that the model has not seen before, right? So by this way, we are somehow estimating what is the performance metric of a model in the test set. So it's going to be somewhere in between, not necessarily below the test or above the test, but it's going to be very close to the behavior of the RMSE of the test set. So this is our RMSE in the cross-validation. So in practice, we use RMSE cross-validation when you want to tune the hyperparameters. And we're gonna see a plot like this again and again for every single model that we cover in this machine learning conceptual course. So in short, we are going to use cross-validation to tune the hyperparameter. And by tuning the hyperparameter, the model is trying to avoid overfitting, get a best combination of model bias and model variance. So here the model is underfitting, here the model is overfitting, And here we know that it's a right fit, right? So let's say it's a perfect fit. Perfect fit. Okay. All right. Now let's talk about the caveats of polynomial regression model and conclude this section. Okay, so imagine this is our data. We're looking at wage versus age. And at the end of the day, you want to predict what's the wage of an individual based on their age. And it seems that there is a nonlinear relationship in the data by looking at these observations, right? The gray circles. And so what are the caveats of polynomial regression model? In general, quadratic loss functions are sensitive to outliers. Remember guys, both in linear regression and in polynomial regression, our loss function was quadratic, right? We were looking at minimizing the MSE, minimizing the summation of, or the average of that, y minus y hat to the power of 2. Now, if you have outliers, then these errors are going to be large. And then we're going to even make that effect even worse by scoring it, right? So in general, quadratic loss functions, which we have in polynomial model, are sensitive to outliers. So this is something that we should be careful. So if I have outliers here and there, then we know that the loss function is going to be sensitive to those outliers. So that's number one. Number two, polynomials have notorious tail behavior. So what do we mean by that? So this basically, look at this example. Imagine this is a polynomial model with, I don't know, maybe the degree of polynomial is 7. Okay. And if in the tails we have some observations, like, you know, we have a bunch of observations here that are pulling up the entire regression, so maybe here, and we have a bunch of observations down here, which is pulling the entire regression down, right? Look at that. The behavior of the model at the tails are kind of weird, right? So for example, what's the story here? So as age increases, your wage is going to increase, and as age increases even more, the wage is going to decrease. But can you explain this part? It goes up and then comes down. So this is also another caveat of polynomial regression model, because again, they have usually notorious tail behavior, especially if the models are unnecessarily complex. And the third one is that polynomial models are global fit. So what does that mean? So let me erase this extra stuff here. Look at the entire data set, right? So these circles are the entire data set. Polynomial model is going to find a global fit for the entire data set. So it says that, okay, this is the entire data set. Let me for example decrease the degree of polynomial. Let's say degree is equal to 2. Let's use actually green. Degree is equal to 2. If I fit a polynomial, it's going to give me something like this, right? So this fit, or maybe even lower than that. But anyways, the idea is that this fit is a global fit, right? It's not going to split the data into different sections based on different values of age, right? So let me tell you what I mean by that. So the idea is that maybe you want to look at the effect of age on wage when age is between, I don't know, 24, 25, right after graduation, and then maybe 65, right before retirement. So you want to use a fit here. Let's say split the data into 3 sections: when age is less than 25, when age is greater than 65, and when age is between 25 and 65, right? So if I do something like this, if I split the data in 3 sections, so I can use different fits, right? So here I can use a fit like this, here I can use a fit like this, and this is what we call piecewise polynomial or splines and local regressions, right? But polynomial itself, as we discussed earlier, it's a global fit. It's going to be something like this. And not always, but sometimes it is not necessarily the best model, right? Because we know that if you know the characteristic of the data, if I can split it in this example into 3 parts, 3 meaningful parts, then by fitting different regression lines to each specific part of the data, I may end up with a better model, which usually that's the case. But we know if you use polynomial model, it's going to be a global fit. Okay, so we're not going to talk about piecewise polynomials or splines or local regressions in general in this course, because those are the topics of statistical learning and econometrics. But here in this course, we will be focusing on machine learning methods. As I said in the very first part of this course, in machine learning in general, we are more interested in predictability of the model rather than interpretability. Okay, so for that reason, we're going to avoid this kind of conversation for this course. All right, until the next video, take care. See you then.